Okay, so we had this, we had this area thing. If you need to, 5C. What was? Yes. Okay. So this is similar to 5B. And we're going to talk today. Our discussion is going to be a lot about this idea of an error bound, which basically means the max error. Where is where does this have to be? How far off is our approximation? Now, did I talk about 5B on Wednesday? I think I maybe did the other class. We talked about error bound. Let's talk about 5B real quick, and then we'll go to 5C. 5B says, what's the error made? It said use R10 and L10 to discuss an error bound on T10, right? That's what 5B says. Okay, so what do we know about trapezoid compared to a left and a right? It's the average, right? So it's going to be in between, right? So if a left is under, a right is over, a trapezoid might be over or under, but it's not going to be over as much as a right or under as much as a left, right? Because it's in between. So now I disagree with the back of the book a little bit. So let's say you did an L10 and it was under, and you did an R10 and it was over, okay? And so you know the exact area is in between here somewhere, right? Now, let's look at the worst case scenario, a lot of what we're going to talk about today. Let's say an I is the exact area. So let's say I was way over here. The exact answer was way over there. R is a little over, L is way up. Okay, let's say we had that situation. Well, we know that trapezoid is in there somewhere, right? Yeah, we actually know more than that, but let's just say we know that trapezoid is somewhere between L and O. Well, what if the trapezoid approximation was way over here? See what I mean? That'd be like the worst case scenario. So what's the most that the trapezoid approximation could be off? With this little example right here. Using these two things right here. The difference between those two, right? The most it could be off. If the trapezoid approximation is way over here and the exact answer is way over here, then the most this could be off has got to be, so we would write that like this, I minus T10 would be less than or equal to L10 minus R10, right? Now, depending which one was bigger, which one was over, so we could actually put brackets around that. You see what I mean? That'd be an error bound. Now, I say we know more than that. Is a trapezoid going to be way over here? Where's it going to be? Exactly in the middle. So now what's the most a trapezoid could be off? 10 trapezoid. It would be L minus R divided by 2, wouldn't it? The most a trapezoid could be off would be half of that interval, because we know a trapezoid is smack dab there in the middle of that. Okay? All right, so that leads us to 5C. So an S20, let's go to a new page. So an S20 is equal to 2 M10s plus a T10 divided by 3. Now, what does that mean? Well, that means if I had an M10 here and a T10 here, where would an S20 be? 2/3 of the way. Closer to which one? I got to think about that. Because I was thinking it was closer to N. It's got to be closer to... It's got to be here. Let's do a simple example. It's a weighted average. Let's take 3 scores. 45, 45, or let's take 45 and 60. Let's do a weighted average of those. So let's count 2 45s and 1 60. That adds up to what? 150 divided by 3 is 50. So if this was 45 and this was 60, 50 would be here, right? So wouldn't it be closer to the one you did 2 of, right? Because that's going to weigh more. Okay. Now, I haven't ever been wrong yet, right? So I except earlier today with Maddie and showed me, but whatever. All right. So, so an S20 is actually going to be a third. Now, I don't think this agrees with what the back said. I'm guessing the back just said, well, S20 is going to be in here somewhere, right? So the most that an S20 would be off would be, right, it'd be less than or equal to M10 minus T10. Is that what the back said? Did the back just say that? If it's going to agree with 5B, then that's what it would say. It would just say the most it can be off is somewhere between M10, but we know better than that, right? Is that what it says in the back? It just has that. Okay, actually, the worst case scenario would be if the exact answer was way over here, right? Then what's the most it could be off? Well, wouldn't that be 2/3, right? Because this would be a third of the way here. So the most it could be off is if I is way over here, so S20 be 2/3 of the distance, M10 minus T10, right? I mean, if we're really going to get picky about that, that's the most that a Simpson's approximation would be off. Now, make sure you understand this notation. This, and I could go ahead here, we did this. So this is the amount of error. The exact answer minus our approximation, that's the amount we're off. And then when we do less than or equal to, we're saying this number over here is the most we could be off, right? The amount of error is less than or equal to this amount. So this number over here is the most we can be off. So that's kind of what we're doing here is we're saying what's the most we could be off? Well, the most we could be off would be 2/3 of the distance between M10 and T10. Okay, and that's if the I of the exact answer is way, way over here. Chances are it's not. It's in here somewhere. So we actually probably have less error. Okay, that's what those were about. That kind of leads into our discussion today. Okay, any others? Any others on there? I know some of you just had to type it into that little program and whatever. Kind of ask some of those questions about error. All right, today, now this is going to be the biggest part of what's on the quiz when it comes to error bounds. I mean, there's going to be a bunch of questions. I hope that this quiz seems easy. Now, we have to do something with differential equations later this week. We're going to do that Wednesday and focus a lot of that on Thursday as well. So there'll be a little more challenging there, a little more calculating to do and so forth. But an easy part of the quiz, I hope, is this stuff here. All the increasing, decreasing stuff. So should we go over those answers? That might be worth just a few minutes. Maybe you guys looked these up already when the sub was here, but let's go through those. Okay, so on 5, or no, are we in 6? Oh, shoot. That's not here. Here it is. So what is that, 29, or where do we start? Yeah, let's do those. So 30, starting with which one? 35. 35, what do you got? Might be true. Depends on the concavity, right? 36. Must, because concave up, so the midpoints are going to be under. 37. Might, it depends if it's increasing or decreasing. 38. Might, same reasoning. Depends if it's increasing or decreasing. 39. Might, same reason. 40. Cannot, because it's concave up. So midpoints are going to be under and trapezoids are going to be over. Okay? 41. Must, since it's decreasing, all the rights are going to be under. 42. Must, since it's concave down, all the trapezoids will be under. 43. Cannot, since it's decreasing, the lefts will be over, the rights will be under. 44. Cannot, because since the trapezoid is the average of L and all, right? And lefts are bigger than the rights are. 45. Must. Yeah, because midpoints will be closer. They won't be as over as much as the ruts. Correct. All right. What was that? 45. 46. Must, because it's concave down, so trapezoids will be under, midpoints will be over. 47. Oh, that's it. We went to 46. Okay. All right. So there'll be some of that. So just should be fairly simple kind of questions with could be a must be true, might be true, or maybe drawing some pictures, but probably not a lot of drawing kinds of things. But what causes them to be over? All right, we really want to get into that today. We're really going to now come up with how the calculators, we're going to do that today, how the calculators know, even though they don't know the exact answer, how do they know they're 12 places accurate? How can they know that? How do we know we're getting close if we don't even know where we're going? All right, that's what we're going to come up with today. So, all right, here we go. So your notes. Now, I'm going to do, as I've done on some other problems that we've done, I'm going to develop these formulas. You do not need to write all this down, okay? You're going to need to know the formulas, and I'm probably going to give you the formulas, okay, on the quiz. So you just have to be able to use the formulas and show your work and use your calculators. So get your calculators out, because that's what you primarily do, don't you? So you have the hats on. So that's going to be a big part of what we're doing, okay? So this part where we're going to develop this, you don't have to write this down unless you want to, okay? All right. So let's start with lefts and rights, okay? Left rectangles and right rectangles. What causes them to be off? What type of function do left and rights fit perfectly? Horizontal. So anything that's not horizontal, left and right, is going to have error, right? What's going to cause there to be more error? Steeper. And we measure steepness by slope, the first derivative. So if we could look at an interval, so if we were doing the integral from 0 to 2, and we were going to do a left rectangle approximation, couldn't we look at the function, look at the derivative, and see when the derivative was a max? Think about that. Let's say the derivative have a max of 3. Max value of 3. What would that tell you about the graph? If the derivative had a max value of 3, what would that tell you about the graph? Well, it'd be an inflection point, but that tells you that the F graph. It'd be an inflection point. That would mean the steepest that it ever is 3, right? Now, what if we then assume that the slope was 3 the whole time? What if we changed that function to have a slope of 3 the whole time? Wouldn't that give us the most amount of error there could be on a left rectangle? Right? Wouldn't that function be the worst case scenario for the amount of error? Would it be possible for there to be more error? No. Right? So that's what you see right here. Here's this blue curve. We're going to pretend right here. Now, does it matter if it's steep positive or steep negative when it comes to the amount of error? It does not. Right? Okay? So let's pretend that right here, this graph has a slope of 3. See, does it look like that's maybe an inflection point? Or whatever the case may be. Let's pretend that this graph had that slope the whole time. Now, this is only one subdivision. This is not from A to B. This is just, say, x sub 0 to x sub 1, let's say. So I'm only going to look at one left rectangle here. So what you see here in black is one, what you see here in black is one left rectangle, right? And then, of course, the blue would be the actual area, right? So this would be the amount of error, correct? Well, what we're going to do is we're going to say, okay, let's find the max of the derivative. We're going to call that K1, and let's pretend that that curve had that slope the whole time. So now forget the blue curve, and let's pretend this is the blue curve. Now, isn't this triangle then the amount of error? Let me make that red. Isn't that the amount that the left rectangle is off? So that area, the red area, is the max error. Okay? Now, let's write that out. So, you guys don't have to write that yet. So the max error would be this right here. Right? That goes on this side. So this is the difference between the exact area and my, I didn't need to put 10 there. 10. So this is the difference between my exact and my left rectangle. Okay? That error is going to be less than or equal to this, what I'm about to figure out, which is this red rectangle right here, or this red triangle right here. Okay? Again, what did I do? I looked at my blue curve. I saw the steepest that it ever was, because I know steepness is what makes left rectangles be off. And I said, let's pretend that that curve had that steepness the whole time. Worst case scenario. Okay? All right. What would be the area of that? Well, it would be 1/2 the base times the height. I did make my box. Okay? So what is the base of this rectangle? Well, that's just one width, right? Remember, this is just one rectangle, right? So the base of this is just one width. Let's call that b minus a over n. Isn't that the width? Call it delta x if we want. Call it h. Sometimes we call that h, and we're going to in the next thing we do here. But right now, let's call it b minus a over n. That's just the width. Okay? And then, what is the height of this? What is that value right there? Now remember, the slope is K1, and K1 is rise over run, right? Rise over run. Well, what's the run here? What's the run here? We just used it. Isn't that this right here? B minus A over N, right? K1 is our slope, right? And so that is rise over run. So what if I multiplied the run over here, K1 times the run, wouldn't that equal the rise? So that's this number right here would be K1 times the run. So this would be K1 times the run. And what did we just say the run was? Isn't that B minus A over N again? So this right here, let's rewrite that a little bit. Let's multiply this. I'd have K1, I'd have B minus A squared, and what would be on the bottom? 2n squared. Now what am I doing? I'm finding this red area. I'm finding the red triangle, right? I just need base times height. Well, the base of it is one width, which is B minus A over N, and the height of this rectangle is the rise here, and the rise is K1 times the run. Rise over run times run. K1 is rise over run because it's slope. Okay? So K1 times the run was B minus A over N. So K1 times the run's got to give me the rise. So that'd be the height of my triangle. So 1/2 base times height. So the red is the most I can be off. And that would be this right here. But that's only for one rectangle. How many rectangles are we going to have? N. So we need to take that times N. So that will cancel with that right there. And what we have just found is our first formula. And by the way, the same line of reasoning would go for the rights as well. And that you can write down right there. And K1, we have to make a note to ourselves here. K1 is the max of the absolute value of f prime. Let me highlight all that in red. K1 is the max of the absolute value of f prime. In other words, we didn't care if the steepest slope was -3 or +3. We didn't care. Negative or positive doesn't matter. But what we had to figure out is what is the max slope of that function. Now that we're going to let the calculators help us with it. Okay? And I'll show you here in a minute how we're going to do it. But that formula right there, and actually I didn't write that quite right. I should have wrote that with a less than or equal to. That should be a less than or equal to. So what we're saying is the amount of error, that's what the left side is, the amount of error has to be less than or equal to that, right? You agree? Worst case scenario? That thing on the right is the triangle amount, the red triangle amount, multiplied by however many subdivisions we have. That's got to be the most we're off. So what that allows your calculator to do is figure out, okay, the most we can be up is this, so therefore we have to be within this range, and you'll see how we can actually make this work. Okay? Now I've got that formula right here. Okay, and so you guys have it written down there. But okay, so that is the same formula for both lefts and rights. Okay, let's go ahead and do a problem and see how that works. So let's do, I don't know if this is one of your homework problems or not, but let's do the integral from 0 to 1 sine of x squared, which of course is one that we cannot do an antiderivative on. We've used this quite a bit. So our question is going to be, now it'll say use the error-bound formulas, or actually in your book it might say use theorem 2 or theorem 3 or whatever. We're not going to memorize the theorem numbers, so it'll be our error-bound formulas. What is the max error for R10? What's the most that 10 right rectangles can be off? So here's how you will work this. So you will say, okay, I minus R10 is going to be less than or equal to, and this is how I'm going to want you to show your work. We got our formulas. You'll have access to those. They'll be probably on the test paper. Where the K1 is, I'm going to put an empty box. And I want you to do the same, and you don't have to put a box, but where that box is, when I grade the quizzes, this is what I'm going to be looking for. I'm going to be looking at what number you put in there for K1. That's going to be the key to these problems. Okay, let's keep writing the rest of the formula. What will go inside? What will go inside these parentheses? How much? 1 minus 0. And what will go on the bottom? 2 times 10, right? 2n, right? So we're using that formula there on the left. Okay, n is 10, b and a are 0 and 1, and the k1 we don't know. So the question is, how do we find k1? Okay, it is the max of the absolute value of f prime. So now we're going to go to our calculators. Okay? All right, is everybody, oh, nobody's connected because I don't have this plugged in. Okay, so let's log in. There you go. Might not be able to right away, but yeah, people are getting connected now. Casey. Dang it, why not? All right. So here's what we're going to do. We're going to we need to figure out f prime. Now, this is going to be a calculator quiz, so you can let the calculator do it. So, Casey, go to your calculator and let's figure out it. It's so easy, I'm guessing you could do it without having the calculator do it, but what the heck? You got the calculator, might as well let it do it. Derivative. So we need f prime, right? No, you could, but I just use that one here. So we're going to do the derivative of sine of x squared. Okay? Now, we want the max of that between 0 and 1, and we really want the absolute value of it. Now, this would be up to you. If you want to do the absolute value, that's fine. It just turns all the negative to positive. But let's don't do absolute value. Let me show you this. So go ahead and highlight that and do a copy. Control C is a quick way to copy. I just meant, highlight it, hit Control C. Now we're going to go to our graph screen. We're going to actually graph it. This will be the fastest way to find the max. I'm not going to make you go through a whole thing of how to find the max, all that stuff. So we're going to go to our graph screen. I delete that. Hit Tab. You can just hit Tab. I think it's a quick way. Hit Tab, arrow up, delete that out of there, and then paste. If you hit Control V, I think, should just paste in what you just had done. There it is. Okay, he's going to hit Enter. So we are now looking at a graph of f prime, but we want to set our window. What would be a great way to set our window? 0 to 1 and do a zoom fit. So go to Window Settings. Everybody's going to have to do this probably multiple times on the quiz on Friday. You're going to have to find this K1 value, which is the max of f prime. So you'll be given the function. It's in your integral. You're going to have to do the derivative, which you don't have to use the calculator for. You can just do the derivative. You know your derivative rules, right? We're going to graph the derivative, and we want to find the max. So he set his window settings. We're going to do it. Set his window from 0 to 1, because that's all we care about, and we're doing a zoom fit. Now, turns out it's always positive anyway, right? What if we'd have had a piece of this graph go up into the positive and another piece go down to the negative? Which point would we care about? Whichever one's farther away from the x-axis, right? So if that graph went up here to 2 and went down here to -4, what number would you want to use? 4. Not -4, but 4, right? Because it's absolute value, so it's going to be positive. Okay? So you could do that. If you graph the absolute value of f prime, then you could just, it'd be the highest point. So it's up to you. So let's trace to that thing. It's nice because the calculator will just tell us when we get to the max. Takes a while sometimes. You could, jump there. If you go like 0.8, maybe it just take you there a little quicker if you can estimate about where it is. And then just arrow until you get that little, right there. Boom. It says max. Okay, now, it's the y value we care about, though, right? So this is f prime. There's our max of f prime. Now, remember, what we're trying to do is worst case scenario. We want K1 to be the steepest the graph will ever be. Would it be okay for me to say 1.2? No. Would it be okay to say 1.28? No. Would it be okay to say 1.283? No. Because 1.2836 is bigger than 1.283. So what do we need to do with that y value? We need to round up. No matter where we decide and what decimal we decide, we need to round up. Now remember, we're doing a worst case scenario. So could I use, as my K1 value, could I use 2? Couldn't I? Is this f graph from 0 to 1 ever steeper than 2? No. Remember, K1's a worst case scenario. Now, should I use 2? I say no. We want to use the most useful number we can that is still the max or the steepest it'll ever be. So we could sit here and argue whether 1.3 would be legitimate. I would rather you go a few decimal places than that. Typically, rounding to the first decimal place is not that good. Now, what if that number there was 58.283? Then going to 58.3, is that okay? I would say that's probably okay. 58.3, 58.4, I mean, you're up in the 50s, so each decimal point is not that big a deal. But when you're just here at 1.2, each decimal place is a little bigger deal, isn't it? 1.2 to 1.3 is a bigger jump than 58.2 to 58.3. You see what I mean? So if you're in small numbers, most of the time we will, but not always, then I think going out, to me, 1.284 would be a pretty good one to use here. On the quiz, if you use 1.283, you will lose points. Right? I want you to understand that what we're picking here is the worst case scenario for the slope. This is f prime. We want a number that the slope will never be greater than. 1.283 won't cut it, but 1.284 will. Okay? That's what I want you to do. We want the most useful one we can. Yes, could we use 2? Sure. Could we use 100? Sure, but it wouldn't be very useful. And we want the most useful one we can while still making it be a worst case scenario. So 1.284 is what I'm going to use. So back to our problem. So I'm going to type in 1.284 here. Okay, now if somebody had 1.29, it would have to round up, right? It was 283. You might say that doesn't round up. In this case, it does, right? So if somebody had 1.29 here, I'd be okay with that. And I would probably even count 1.3. You know, but if you rounded that to 2, to me, that's too much. That's not good. Okay? All right. So let's work that out. So we get 1.284. The top, of course, is just that, divided by 20. Right? And what's 1.284 divided by 20? 0.0642. That is the most our R10 approximation is off. Right? That's the most it's off. Now, what could we do with that? Maybe they might say, give an upper and lower bound. Well, since this is R10, we could go to our calculator document. Remember this guy here? So we could go to our calculator document. They say, what's an upper and lower bound for the exact area? Well, we could go to our calculator document here, run the RAM program. We could type in, let's say we want to go 6 decimal places. Okay? We're going to type in sine of x squared. We're going to go from 0 to 1. We're going to do 10 subintervals. And there's a right there, 0.353244. 0.353. So R10 on this one is 0.353. What was it? 244. So don't we? And if this is the most we're off, right? See what we just did here? This, because of the work we did back here, we came up with this formula. The most that those right rectangles are off is this. So we know the exact answer. What can I do with that? What can I do with this? Plus or minus that onto this. I could take if this is under, I could take 0.353244 and add on 0.0642. And whatever that would be. And then I could subtract this from 0.353244. And I would know that the exact answer has to be somewhere between them, right? That's one thing I could do. We don't do that a whole lot, but that's one thing I could do. Understand what this number means. That's the most that this is off, which tells me, because of this 0 here, it tells me I must be good in that first decimal place, right? It gives me an idea of how accurate I am. Remember we said we want to figure out how the calculator knows it's 12 decimals accurate? This right here tells me it's got to be at least 1, but you know what? It's probably more than that. It's probably more accurate than that. But what this tells me, so when the calculator gives you an answer and says this is accurate to 12 decimal places, it's probably accurate to even more than that if we can see them. but we know it's accurate to 12. Okay? All right. It's kind of like I started. So we talked about if you don't know where you're going, how do you know how close you are? Right? Well, in this case, we don't know where we're going, but we know we're within 12 decimal places because that's what this number tells us right here. Okay? Because we knew the worst case scenario. That's the key. We knew the worst case scenario. So now, if I take off on a trip and I don't know where I'm going, but I know I'm only going to go 1,000 miles, well, then as soon as I take off, I know I'm within 1,000 miles, right? As long as if you could get a little bit of information. Well, here we're getting a little bit of information. Okay? We're getting a little bit of information. We're getting this worst case scenario. Okay. Now, because I just think you guys are good students and you should see this, I'm going to go through how we do midpoint and trapezoids. Now, again, you can put your pencils down for this if you want to. Okay? But I think the algebra and the stuff is kind of cool to see. Okay, so we're going to do something similar to this. Except now with a midpoint and a trapezoid, what causes it to be off? Concavity. The more curvy, remember that discussion? Well, what causes curviness? What measures curviness? What derivative? The second derivative measures curviness. The bigger the second derivative is, the more curvy the graph is. So what we're going to do is we're going to assume K2, 2 for second derivative, the 1 in K1 means first derivative. We're going to assume that K2 is the max of f double prime. In other words, we're going to take our function, the sine of x squared, and we're going to figure out when is its second derivative the most. When is it the most curvy? And then we're going to assume that that graph is that curvy the whole time. Worst case scenario. Here's what this would look like then. If the second derivative is K2, then the first derivative, wouldn't it be K2 times x? Right? Antiderivative plus c, we don't care about. And then do the antiderivative again. You'd raise that up to a 2, divide by 2. Wouldn't this be the worst case curve? Remember in the last in this one, we just assumed if the slope stayed this whole time, this is what our curve would be. Well, what we have here is a parabola that's the most curvy that this could be. This would be our worst case scenario graph. So the max error is going to be the difference between this area, like this curvy parabola, and our trapezoid, right? We need to subtract those, and we need to find that. That's how much we're going to be off. That's the idea. That's what we're going to do. Okay? Well, the first thing I have to do then is figure out, we're going to let this go from 0 to h. We're going to do one subinterval. Remember how we did that on the last one? We just said, let's look at one subinterval. Okay? So we're going to look at one subinterval, one midpoint, one trapezoid. So we're going to call that h. That'll be easy. Now, h is just going to be b minus a. So h at the end here is going to be b minus a over n, right? H is going to be one width. Okay? 0 to h. So we're going to do the integral from 0 to h of this guy right here. That will give us the area. That will give us this area under that parabola. The curviest parabola we could have in this problem. Okay, worst case scenario. Okay, let's do it. So we're going to raise that up to a 3 and divide by 3. Would give me what? 1/6. K2 is just constant, just hangs out there. X cubed from 0 to h. So that'd be 1/6 K2 h cubed minus, and then we plug a 0 in, that'd just be 0, right? Okay? That is going to be the amount of area under the curvy parabola, right? Now we need to get the area of one trapezoid, okay? Well, one trapezoid would be this y value and this y value plugged into the curvy parabola. You with me? Hang in there, Casey. With me? I'm going to plug a 0 into the curvy parabola and plug an h into the curvy parabola, right? That'll give me these y values. So my trapezoid is going to be 1/2, a 0 plugged into the curvy parabola. What's that give you? 0. And then an h plugged into the curvy parabola. 1/2 K2 h squared. Right? Times right? Isn't that going to be the trapezoid area? So that's going to be what? 1/2, forget that. So that's going to be 1/4 K2H cubed. So now I got to take this minus this, right? This is my exact area under the curvy parabola. This is the trapezoid area. Subtract them. Won't that give me the amount I'm off? Okay. So what's 1/4 K2H cubed minus 1/6 K2H cubed? What is that? 1/12, right? It'd be 3/12 minus 2/12. Because they're like terms, aren't they? Right? 1/12. Okay, we just found our first formula. Now you can write. We just found our first formula. So the exact area minus this has to be less than or equal to, because this is our worst case scenario, 1/12. Now we don't want to write it like that. That'd be 1/12 K2, and then what did we say H was? What was H? B minus A over N cubed. Oh, but wait a minute. That's only for one subdivision. How many subdivisions we have? We got to multiply that by N. So what's that going to make? It's going to make this N cubed on the bottom turn into N squared. Okay, so how will this look? It'll be K2 on top. It'll be B minus A cubed on top. And the bottom's going to be what? What's the bottom going to be here? 12N squared. Because this will be N cubed, and then this N will cancel that. So this is going to be 12N squared. Okay? Now we got to do midpoint. It turns out midpoint is not the same as trapezoid. And we know that because remember when we said midpoints were roughly twice as accurate? Remember that? As trapezoids? That's why we did that funny thing with Simpson. So I'm not going to go through it, but it'll end up being K2 B minus A cubed. And what number are you supposed to be on the bottom since it's twice as accurate? It means it'll have half as much error. Well, it's got to be one. It's either got to be 6 or 24. This is the amount of error, max error, and we said a midpoint's going to have half as much error. So it's going to be 24. And there's our two formulas. Whoops, that's not supposed to be a 10. I don't know why I keep putting 10. M. So those will give us, but again, just so you understand the max error idea. The key is the K1 and the K2. Okay? Steepness causes error on left and right rectangles. So K1 is the max steepness. Worst case scenario, the most amount of error. Midpoints and trapezoids are off because of concavity. The more curvy, the more error. K2, the second derivative, measures that. So we're going to do the max K2 and use that and pretend that the curve has that the whole time. So therefore, that amount of error will be the most we could be off with our midpoints or our trapezoids. Okay, so when you work a problem like that, it's going to look just like, did I do that right? It's going to look just like this, except when we do the K2, when we go to our calculator screen, we'll be graphing what? The second derivative. So if you're doing midpoints and trapezoids, you'll be graphing the second derivative, not the first derivative. So let's do a problem where we have to do that, but we'll make a little twist in this. So let's take that same function we just had. Casey, you're still a presenter. And here's where the calculator really does its magic now as far as how it gets this answer. It's more in a problem like this. So we're going to change the question. Instead of saying what's the max error, which means just use the formula, okay, we're going to ask this question. How many subdivisions are needed question mark This would be, we're asking the question, how many subdivisions, how many midpoint rectangles do we need to do to guarantee we're within 0.005 of the right answer? In other words, 2 decimal place accuracy. That's what we want to do. We want to use this formula to tell us how many subdivisions are necessary to get 2 decimal accuracy. And remember, we don't know the exact answer, but we're going to use the fact that we can take our worst case scenario and we know we can find what n is that will give us guaranteed 2 decimal place accuracy. Now, chances are, since we're doing a worst case scenario, we'll probably get more than that. We'll probably get more decimal place accuracy than 2 decimal places. But we're guaranteed to have 2. Okay? So we set it up very much the same thing. The only difference is, what don't we know here? Think about this formula here. What won't we know in the formula? We won't know the n. But what will we know? That number there. We want it to be what in this problem I just wrote down? 0.005. So we will simply take our formula. So box, I don't know what goes in there. It's going to be K2 because this is midpoint now. So midpoint trapezoid, we use K2. Left and right, we use K1. Okay, what's going to go in here? One minus 0. What's going to go down here? 24n squared. And over here, and it is okay to just do equals when you do your work, and then we'll talk about how we adjust that for the greater than sign in a minute. And then over here goes, and those are really the only 2 questions I'm going to ask you using these formulas. In one case, I'm going to say, what's the max error for 10 rectangles, 20 midpoints, whatever. Then you'll know the n, and you're going to come up with that number over there. Or I'll say, how many subdivisions do we need to get within 0.005? All right. Well, now we need to fill in this. This is K2. K2, remember, is the max of f double prime. So, okay, so you're up again. So now we need the second derivative. Oh, he did it already. He did the derivative of the derivative. Now go to that menu option by the 9 there. Yep, yeah, this one right here. Hit that. This right here will do the second derivative for you right away. So if you were doing a problem and you just needed K2 instead of doing the derivative, then doing it again, you can just do the second derivative right away. It's up to you. But we already done the derivative, so go ahead. And so there he's got a second derivative, so let's copy and paste it. You don't have to copy and paste. You can just type it again, whatever, write it down, type it in. I don't care. So we're going to go to our graph screen. We're going to graph that. So we're going to delete that, paste it in there. Oops. Go ahead and paste that in there. We want to be from 0 to 1 again. So a big part of studying for this quiz is making sure you can do all this on your calculator, right? So we're already set from 0 to 1. So we already got our x from 0 to 1. So he's just going to do a zoom fit. Now remember, we got to check the negative and the positive, right? So we could just type in a 1 right now in the trace. He's got to go to trace, I guess. He could go to trace and type in a 1 and see what that number is way over there to the right. And we might jot that down, negative 2.285, okay? And then type in a 0. It looked like it was, and that's just 2. And then go to the right a little bit. Keep going. It looks like it's not actually 2. It's, okay, now it's going down. So what number do we want? We want that one way out at the right, wasn't it? So what was it? Type a 1 again. Let's go back to that number. So what do you want to use, you think? What should we put into our box? You could go 2.2853. That'd be okay. That's probably more than you need. I would say 2, because we're so used to 3 decimals, it's not a bad way to go. 2.29 I'd be okay with. But how about 2.286? Right? Keep in mind, this isn't about rounding. Don't get thrown off. You say, well, why did you change that 5? That's a 2. You don't round that up. Yeah, we do in this case, right? We want the worst case scenario. So 2.286 would be a good one to use. And positive 2.286. Now, if you want to go 2.29, I think that's reasonable. I'd be okay with that. Okay? I'm going to be looking, so you're going to have to show your work when you're doing these problems. Okay? And I'm going to be looking at what number you have right there. Okay? And then compare that to your answer. All right, so basically now we need to solve this. Now, you could go ahead and start solving this kind of on your own, or you can use the solve feature of the calculator. Right? So we could just type this right into a solve on our calculator. So, Casey, let's do it. So let's go to the calculator. We're going to do a solve, and he's got 2.286. Of course, 1 minus 0 cubed is just 1, so there's no need to put that in there, but some problems that will be important. He's going to use an x. Wasn't it x squared, I think? Yep, we got to make sure and square that. You could use an n also. Equals, it's okay to go equals 0.005. Comma x, right? You got to tell what you're solving for. Now, Casey, go ahead and copy, grab that again, and instead of doing an equals, do a less than or equal to there. And let's just show what it means, what happens. I would personally, it's supposed to be less than. I think the formula says less than. And then hit enter. Okay, so doesn't it make sense? Now we're going to throw out the negative one, because what are we looking for here? What are we finding? What is n? Number of subdivisions. So what would be an acceptable answer to this question? 5 subdivisions. Do not put 4.4, 4.364. We don't have decimal subdivisions, right? Whole number subdivision. And so if you use an equal sign, it comes out here in equals, but you got to understand what you're finding. You're finding number of subdivisions. We've got to always round that up. 4 subdivisions won't do it. It takes 4.36, right? So 5 midpoints would get the job done here. 5 midpoints is guaranteed to give us 2 decimal place accuracy. Now, chances are it gives us more than that, but it's guaranteed to do that. Okay, so 5 would be the answer I'd want to see as your final answer. Okay, would a number bigger than that? Would 10 do it? Yes. Would 20? Would 100? Right? But the answer I want to see would be rounded or just bumped up 1 to the nearest whole number, not the nearest whole number, but the next whole number up from whatever decimal you get here. Unless it comes out exact. Chances are it doesn't come out exact. Okay? There you go. So these are called the error-bound formulas. The key is K1 and K2. You use K1 when it's lefts and rights. You use K2 when it's midpoints and trapezoids. But it all comes from this stuff we talked about here. Increasing, decreasing slope is what causes left and rights to be off. Concavity is what causes these to be off. And that is how your calculator is programmed roughly. Just think about what it needs. When you type in the integral 0 to 1 sine of x squared, it needs a b minus a. What it's doing is this problem right here. It's programmed to do 12 decimal place accuracy. So internally in the calculator, it says, okay, he's giving me this function. I can find the second derivative of that. Calculator can do that. It can set up and find the max of that in the window 0 to 1. So it can find that 2.286 number. It can be programmed to find that. It can do all that. We did use our calculators to do it all. It's got the 0 and 1. It can plug that in, the 24-inch squared. It can solve that equation. It can see how many subdivisions it needed. This was 5. And then it can run, just like our area program does, it can run an approximation. Now, it probably does something more like Simpsons or something, so it doesn't have to do a ton. Because it wants 12 decimal place accuracy. What do you suppose we'd have got here for 12? Let's see how many midpoints that takes. Casey, all you got to do is change your formula real quick. Instead of 0.005, let's put 12 zeros there instead of 2. Okay, it needs 436,464 midpoint rectangles to get the job done. Now, if the calculator had to do that many subdivisions, it would take a while and it would be slow. Simpson would be much faster. There is a formula for Simpson. We're not going to do it. It involves the fourth derivative. Simpson's rule is the max. It's a K4. It needs the max of the fourth derivative. But it would need far fewer. And so it could just run like that area program. It could just run a quick Simpsons with 6,000 subdivisions, boom, 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 and then it gives you the answer. Okay? So all that is programmed in. When you type in, go ahead and do that for us real quick. Type in sine, just do the integral, Casey. Let's do the exact answer to this. So the integral of, no, the other one. Definite integral. There you go, definite integral. Okay? Let's go 0 to 1. Sine of x squared. So when he hits enter, between the time he hits enter and the time the answer pops up, which is a short amount of time, it was doing those calculations. Okay? It was doing those calculations. So that's why it gives you a decimal, because it did an approximation technique guaranteed to give us 12 digits. I think there's 12 there, isn't it? 12 digits of accuracy. Could be more. Okay. All right. So your homework for tomorrow is the 6.2. On the thing there, you're going to be, again, when it says use theorem 2 or theorem 3 or whatever, it's talking about these formulas. Okay, these formulas right here. Okay. The error-bound formulas or the theorem. I can't remember exactly what it talks about in there, but